All right, welcome back to 4.3. This is part 2. We want to answer questions about a graph or graph, an equation using its vertex, its axis of symmetry, and its intercepts. And so, in other words, if you're given that information, can you graph and more, I guess, just as importantly, find the equation? All right. So we're given this equation, and what can we answer? Since A is -2, B is 4, and C is 2, well, the only one we care about the sign on is A. Since A is negative, the graph is concave down. Let's see, find the domain and range. Well, the domain is going to be -infinity to infinity. It's just that domain are the x values, so the domain is the numbers I can put in here. Well, I can put in any number into a polynomial and it won't give me an error in a calculator. And so this is our way of saying any real number. We will need to find the range. Now, this is a different question than concave up or concave down. Where is it increasing? Where is it decreasing? Where is the graph positive? Or is f of x, or where is y positive? Sometimes it helps to replace f of x with y to clarify your thinking. And when is y less than 0? All right, so we'll get all of these questions. All right, so the first thing is, since A is negative, right, the graph concave down. They could have completed the square, but they're not doing that. They use this formula to find h. And once you find h, you can find k by plugging the h that you found into the function. So I've gotten these questions not that infrequently, like, is it always f of 1? Well, every time h is equal to 1, it's f of 1. But the answer is, no, it's not always f of 1. It's always f of whatever h was. So this is one of those situations where you have to do part 1 before you attempt part 2. Don't try to find f of h without finding h. That sounds kind of obvious, but it's a question every semester in the live lectures, in the live classes, that students will ask, like, well, where'd you get the 1? And I'll have to point to it right there. It's not always 1. I had to calculate the 1, and I calculated the 1 because I used this formula. So just to clarify. So running that calculation, you find k is 4. So the vertex is 1, 4. Again, once I find the vertex, or once I find h, I know that the axis of symmetry is the line x equals that number, x equals 1. So from this one to that one. So remember, the line x equals 1 is a vertical line. So we have all this information about the graph. The y-intercept is f of 0. Okay, this is true. You let x equal 0, or you plug x equals 0 in, and that's going to find the y-intercept. So you do that, and you find it's 2. So they'll say the y-intercept is 2, or if you're using interval, or if you're using an ordered pair, x is 0, y is 2. That would be the y-intercept. The x-intercepts are found by solving the equation f of x equals 0, or what I was saying, ax squared plus bx plus c equals 0. So on this particular problem, it doesn't factor. So we bring in the quadratic formula. They get, well, for the exact values, 1 plus or minus the square root of 2, which they ran through a calculator. And so we have 2 x-intercepts. The exact values of the x-intercepts, by the way, are 1 minus square root of 2, 0, and 1 plus square root of 2, 0. Sometimes we are very interested in exact values, so I wanted to point that out. So we're putting it all together. we have our vertex, I'm calling V. We had this point, which we knew was our intercept, or y-intercept. Remember the minus 0.41 and the 2.41 that we got? The axis of symmetry going through here. This point wasn't mentioned, but it's a bonus point. When we have the axis of symmetry, what that means is, if you know one point on one side of that line, we have another mirror image on the other side of that line. All right, so we have a surprising number of points here just from doing things we kind of have been doing ever since we started algebra, meaning, evaluating a function. I did what, f of 0, f of 1, because I wanted to find these points. Just plotting these points on the number line that we calculated with something we've been using for a while in previous classes, I assume, the quadratic formula. So we're using these things to get a lot of information about the graph. All right, the one thing I hadn't answered yet was the range. So I already told you the domain was all real numbers, which in interval notation, negative infinity, infinity. But how about the range? Well, this graph has a maximum y value right here, meaning y is equal to 5, y is equal to 6, but the graph doesn't go above 5 or 6. It doesn't go up to those values. The maximum the graph ever takes on is 4. So 4 is the maximum, and the minimum, negative infinity. This graph keeps on going. There's a lot more questions they could ask. All right. When is the graph increasing and when is it decreasing? All right. Well, the graph is increasing from left to right on this piece right here. And what I want to do is I want to look at the number line and see where that is. So on the number line, the graph is increasing from negative infinity to 1. So that's where the graph is increasing from negative infinity to 1. Where is it decreasing? Well, it starts decreasing here. So if it starts decreasing here at 1, and then it keeps on decreasing forever, we would say it's decreasing on the interval from 1 to infinity. And you can see these numbers are repeating themselves. This right here, this 1 was h. And let me back up here. This maximum, or the 4, was k. I'm not saying k always goes here. You could have infinity there and k here, so the conditions were different. But, k showed up for a reason. 1 showed up for a reason, or h showed up for a reason there. And what were the next questions? Next question is, when is the function greater than 0? All right, well, the function's greater than 0 anytime you're in quadrant 1 or quadrant 2. That's when the function is greater than 0. So the function is greater than 0 on this interval between the intercepts. So they wrote it this way. I will warn you, your book will more than likely write it 1 minus the square root of 2, comma 1 plus the square root of 2. Exact values are just sometimes more popular than these calculations rounded to a certain amount. I actually haven't checked. I think both might be possible. All right. When is the graph less than 0? When the graph is less than 0, that would be on this interval and this interval, because you pick a number like 2, the graph is below the x-axis, or negative. So we have those two intervals, and I'll just write it right here. So what am I saying? If this were an x-intercept, I called x1, and this were an x-intercept, I called x2, the interval we're talking about is negative infinity, comma x1, union x2 comma infinity. Now I'm not writing this down so you memorize it, but I'm just saying that it's no coincidence that these were answers to a different question as well. These were the intercepts. The intercepts tell us the breaking point between the graph being positive and the graph being negative, and that's because at the intercepts the graph is equal to 0. All right, one more. This is a different graph. So I kind of recognize this one as a perfect square trinomial, right? This, if you were to factor this, but we'll see what happens. All right. So actually, I kind of jumped out of that, but I'm saying this is f of x equals x minus 2 squared. And so this is kind of like a problem where the completing the square happens on its own. In other words, it's already a perfect square. If I match that up, which I'll do a bit later, with the formula y equals a x minus h squared plus k, the a will reveal itself, the h will reveal itself, and even the k will reveal itself from just knowing how to factor this. But the book did the whole analysis, and instead of taking advantage of completing the square, takes this problem, same problem as we're going to, and does the formula. The formula tells you h is 2. You take that 2 and plug it in, and it tells you f of h is equal to 0, and so we know our vertex is 2, 0, and the axis of symmetry from there. We'd need to do this regardless of what method we're using, we'd need to do this. To find the intercept, let me make a little table here. You're going to put in x equals 0, and you're going to calculate the y value from that formula. And if you calculate the y value by plugging it in, 0, if I put in a 0, that's 0, that's 0, I get a 4. So that's the intercept. We'll call that point A. All right. We found the vertex earlier. How did we find the vertex? Well, they found H, plugged it in, got 0, and that's the point I'll call V for vertex. And just those 2 points is all they used, because you get this bonus point that we never even put on the table using the axis of symmetry. So get an additional point, they call it, by going to the other side of the axis of symmetry. Domain, always set of all real numbers, or negative infinity, infinity. I'm just saying that's the domain anytime you have a polynomial, unless there's some reason, where they restricted it for some reason. You can put any number into the equation you like, and you won't get an error. But the range is where you look at the y values and you find the minimum y value and where it goes from there. Well, the minimum is 0 and the maximum infinity. Where's the function decreasing and increasing? Again, that separation between where it's decreasing to where it's increasing is going to occur at x equals 2. And so, no coincidence that this point is h. All right, so it's decreasing, it's increasing. And what's the last thing they ask us? Where is the graph greater than 0? F of x greater than 0. Well, it's equal to 0 at 2, but everywhere else it's greater than 0. And so you could say it's greater than 0 everywhere except where x equals 2. But they went with interval notation on this one. Not unusual for this type of problem. And so basically they're saying it's the entire number line, but if you just take one point out of the number line, there are two intervals. This interval has a minimum of -infinity and a maximum of 2, if 2 is the point you removed. And then this interval has a minimum of 2 and a maximum of infinity. And so that's what they're writing here for the answer to the question, when is f of x, or the solution to f of x is greater than 0. The graph is never less than 0, so that would have no solution. All right, yet another example. F of x equals 3x squared plus x plus 2. We want to determine the graph. If the graph is concave up, concave down, you know the drill from here. So ax squared plus bx plus c. A is equal to 3, b is equal to 1, c is equal to 2. Since a is positive, the graph is concave up. Now this is going to be a very tight thing to graph, but the computer can do it. When I say the computer, I mean the computer the book uses. But you plug this in and you find out that h is equal to -1/6. So that's going to be a shift, not a shift of 1 right, to the right, but well, actually, since it's minus, it's to the left. H is minus. So it's going to be a shift, just a tiny shift this way, of the vertex being through the y-axis. All right. Well, you take the -1/6, plug it in, and you get 23 over 2. Now 24 over 2 would, or sorry, 23 over 12. 24 over 12 would be 2. So this is very close to 2. But we found the vertex. That's enough to get started. They went ahead and found out that there are no, they used the discriminant test to find out there are no no x-intercepts, but I think that would have been, I think I said earlier, I think that would be unnecessary in this case. So what are we doing? It's really tight quarters here. But they plotted that ordered pair, -1/6, 23 over 12, right here. And then they knew that this graph was going to open this way. So all we really needed was just one more point on either side of the axis of symmetry to know which way it's going to open. Now, it's no coincidence they picked that nice point, 0, 2. It's really tight quarters, but they picked that point because it's an easy point to plot. In fact, I kind of knew that point was on this graph before I even started working on it. If x is 0, I'm going to get f of 0 is 2. So 0, 2. It's not the vertex. It's very close to the vertex, but it's the y-intercept. So it's a very easy point to calculate. And that's really what they based this whole thing on, it looks like. Sorry, yeah. Well, I will say math books don't really care how close things are. They wouldn't say, oh no, now try a point, now try plugging in 1 and seeing what you get. Computer software and math books, even if the points are tight, we'll pretty much leave it there. All right. And the last thing are they asking? Let's see. Oh, next thing they're asking is the domain. Again, they keep asking the domain, and the answer keeps being all real numbers. And then the range. And remember, it's minimum, comma maximum, and the minimum is k. So k comma infinity is essentially in interval notation is the range. Where's the function decreasing? This is working out to be a good example because you really have to rely on, not just your picture, not just your memory, but the fact that these numbers repeat themselves. This is h. It's decreasing from negative infinity to h. So it's decreasing its entire domain up to from here to here. And then it turns around and starts increasing. So you can see the connection. Again, this was just h. As soon as I knew h, I could have just said, oh yeah, it's negative 1/6 infinity. I would also need to know whether the graph is going up or down to get, which, concave up or concave down, to know which part it's decreasing or increasing. So, but a quick sketch is helpful. All right, something you're asked to do on more than one occasion on the homework is something like this. You're going to be given the vertex and one other point, and you want to find the equation of the graph. All right, so if you're given the vertex, you're essentially given h and k, but you're not given a. And that's going to be the missing point in this calculation. So here it is. Determine the quadratic function whose vertex is negative 3, 7. So again, I know h, I know what to substitute for h, I know what to substitute for k into this equation. So they substitute the value for h, substitute the value for k, and we have this a hanging here. We still don't know what that is, but they gave us enough information to find it. They told us the y-intercept is 2, which means this graph goes through the point 0, 2. So we're going to substitute 0 for x and 2 for y, or f of x, and you'll see that on the next page. X got replaced with 0. F of x, you think of f of x getting temporarily replaced with y, and then that y getting replaced with a 2. And all of this was so we could solve for y, solve for a, and put the a right there. Turns out the a was invisible. It was 1. And so the problem was correct without writing anything there. But we had to go through that process. All right, removing the parentheses, combining like terms, we can write it yet another way. All right, so we see what happened, right? The vertex, how the graph was oriented, the intercept. All right. It's a lot of questions, and at the end result, we get a graph, but they're going to ask a lot of these questions along the way, so be prepared to answer the questions. Finding the maximum or minimum value of a parabola, of a graph, that occurs at the vertex. So, and be careful how the questions are worded. I don't think I have many of these, if any, because it's kind of a pre-calculus concept, but let's look at this. So we have this parabola. It's got this vertex h, k. And k is the minimum of the graph. What's h? H doesn't really have a name. It's not the minimum. I call it the minimizer. H is is the point that gives you k in a table. You put in h, you calculate k. So in other words, if I put in 3, I will, let's see, calculate the answer, and I'll get negative 12. So 3 doesn't have an answer. They just say the minimum occurs at x equals 3. But what's the minimum? The minimum is k, or the minimum is negative 12. So all of that work was to find that point. Like I said, that's more of a calculus thing, or pre-calculus thing, finding the maximum or minimum. This is also going to be important. We also will talk about turning points. And it's extremely rare without calculus to be able to find the turning point of a graph. So in a future chapter, we'll have something where a graph might go like this, degree 3 or something, and it has 2 turning points, turning point 1 and turning point 2. And if a turning point just happens here in the middle of in some quadrant somewhere, we can't find it in this class. It requires calculus. So what the book is doing is kind of foreshadowing by asking us to find turning points when we can. So this turning point, they're not calling it a turning point, they're calling it a minimum or whatever they're calling it. But this turning point is a big deal because we can find it with, fairly simple tools. So I just want to explain why it's here. You don't need to know that to get these problems right, but you just might want to be aware that minimums and turning points, big deal in some other math classes around this level. All right, well, it took a long time, but we finished 4.3 quadratics.